We are going to perform another optimization example with Nastran Solution 200. My name is Christian Aparicio and I'll be going over today's tutorial. Today we are going to focus on a normal analysis example or eigenvalue analysis example. On the next slide, we are going to cover the goal. So here we have a built-up structure on the left. This is our starting structure. By the end of the structure, we are going to vary some of the structural dimensions, and we are doing this because we want to minimize the weight of the structure as much as possible while ensuring the first natural frequency is above a certain frequency. This example can be found in the MSC Nastran Design Sensitivity and Optimization User's Guide. If you look in Chapter 8, there is an example called a vibration of a cantilevered beam. So if you want more details, you can refer to that guide. Let me see if... Actually, the one file I wanted to show you is the lecture. So let me go ahead and show you that right now. So this is what I plan on covering. I'll give you some feedback regarding the model. It's always good to know how it's constrained, if there are any materials, loads, and all that good stuff. I then will cover the optimization problem statement. And this is, think of it as a requirement. This is a summary of everything you're going to vary in the model. It's your objective, it's your constraints. Once you have this developed, you can then start preparing your model for Nastran Solution 200. So I'm going to show you each step you need to take in order to convert your BDF file to Solution 200. After this, we'll go ahead and perform the optimization, and then we'll go ahead and look at the structural results and the new optimized results towards the end. And then at the very end, we are going to update our original model with optimized structural dimensions. So just in case you're a professional engineer or student, here's my contact or my email address. If you want access to the web app, you are more than welcome to contact me. If you are a professional engineer and would like to ask some questions regarding additional training, some general questions, you can also contact me at this email address and I will get back to you. Now, like I said earlier, you'll find this example in the user's guide. Let's go over the optimization problem statement. Here on the left, I have a summary of the design variables. Here you can see each color represents a different structural dimension, if you will. Here, this first section, we'll call this section PROD 201. We are going to let that cross-sectional area vary. We are going to repeat this for the green and the blue sections that you see me highlight with the laser pointer. We are going to say that these three areas, and you'll see that the three areas are also shared with the elements on the underside. We are going to let these areas vary between 0.01 and 100 units of area. Also, here in magenta, blue, and yellow, we are going to let the thickness of these three sections also vary. Here are the range of thicknesses that we are going to allow. Now let's talk about the objective and the constraints on the right-hand side. Your finite element model will produce a large quantity of results. You're going to have multiple natural frequencies. You're going to have different mode shapes. The list can go on and on depending on the analysis type. What we're going to do is we're going to set the weight as an objective. We want to minimize the weight as much as possible. One thing to keep in mind, it's not visible here on this screen, but if we look at the profile view of this structure, there are point masses at the nodes, if you will. These point masses constitute a large portion of the weight. So what we are going to do for the objective is we are going to say that take the entire weight of the structure, so this will be represented by A1, and then subtract from it 90 units of weight. These 90 units of weight are from the point masses that you find at these points. So the reason we are doing this is because we are going to vary parts of the structure that are not the point masses. So just to ensure that the sensitivities have some level of sensitivity, we are going to subtract the point masses from the objective equation. Keep in mind, we're not removing the point masses from the model. We're just removing their contribution to the objective function. Number 2, the design constraints. We're going to say that the first natural frequency should always be greater than 20 hertz. This is a fairly straightforward example. We're going to go through first obtaining the BDF file, and then I'm going to go and walk you through the process of setting this up for Nastran Solution 200. We are then going to look at the results, both the structural and the optimization results. And then, like I said earlier, we are going to look at the optimized parameters. So the Nastran Solution 200 web app is the enabler for this tutorial. This will help you take your BDF file and convert it to Solution 200. Let's go ahead and start with the BDF file. You may have a model of your own that you built in your pre-post processor. Here, for example, I've gone ahead and constructed this model for this tutorial. If you want to follow along, you'll find this example in the user's guide. So starting in the homepage from the web app, go to the user's guide and go to the size optimization tutorial section. And then you'll find this example called vibration of a cantilevered beam. This is the one you want to go ahead and download. So right click on the link and save the link as. We'll go ahead and drop this on the desktop. So this BDF file that I've just downloaded is the same model I have in my pre-post processor. If you open it up, you'll find all the information about the material. You'll find information regarding the constraints. I believe that is up here somewhere. You'll find information regarding the cross-sectional areas. That's also included here, and so on and so on. So this is all contained in this one BDF file, and this is our starting point for this tutorial. So from the home page, open the size web app. Here, what you're going to want to do is upload this BDF file so you can start the conversion process. You'll notice that there are 3 sections at the top: the variables, the objective, and the constraints. These are the 3 sections we are going to use throughout this tutorial. Here is a long list of properties that have been identified by the web app. The first 3 design variables I want to set are for the area. So I'll go ahead and click 1, 2, and 3. And the next table are my design variables. And let's go ahead and use the bounds that I mentioned in the PowerPoint. So 0.01 and 100. And this completes the creation of the area design variables. It's not focused on the 3 thicknesses. Here, if I jump back to the lecture, we just defined the area design variables for section 1, 2, and 3. We are going to now define the thickness design variables for section 1, 2, and 3. So let's go ahead and do that now. So here we search the table for T's. We'll go ahead and set these 3 properties as design variables. You can see that the labels are in the label column. The newest 3 design variables have labels x4, x5, and x6. So let's go ahead and update the lower and upper bound here. And then 2.0. Just go ahead and update all of these bounds. And let's go ahead and refer back to our optimization problem statement. Remember, it's very important that you have this problem statement defined. When you're going through this conversion process, it makes the process a lot easier. So once we're done with variables, let's go to the objective section. This is where we want to create what's called a custom equation for the objective. So in order to create this custom equation, click on switch to equation objective. This is where you can type in your custom equation. But first we have to specify this quantity called A1. This quantity represents the entire weight of the structure. So let's go ahead and scroll down and click on this plus icon to create a new response called A1 that corresponds to the weight of the structure. we can then come to this custom equation box, type in the label, and say A1 minus 90, where 90 is the weight of the point masses in the model. Here, since I have Patron, I can actually show you what the point masses look like. So here you can see these triangular elements that represent the point masses. Now let's go ahead and move on to the constraints. Remember that we want to constrain the natural frequency. So here is a row called frequency. Let's click the plus icon. And here we want to constrain the first natural frequency. And the lower bound will be 20 hertz. So we will type in 20 there. And now let's go to the exporter and extract both the model that you see here and the design model that you see on the right. So this first option is going to download the zip file. We are going to go ahead and extract these results. You see that there's a model file. This is essentially the same model as before. The description of the materials here, the cross-sectional areas are defined here. So the entire finite element model, this whole model, is contained in the model PDF file. But remember, it's been converted to solution 200. In the same directory is the design model. This has information regarding your design variables, your objective, and your constraints. Here, fortunately, there's a third file. It's a shortcut. This shortcut, when executed, will automatically start Nastran, and it will start a status page where you can monitor where the optimization is at. After the optimization is complete, a new page will show up. This page will show us the result of the optimization. The first thing we want to review is this top message, run terminated due to hard convergence. This is a successful message as indicated by the green checkbox. Remember, this objective plot is showing us the objective value. So here, if we look back at the problem statement, we see that for the very initial design, the value of A1 minus 90 gives us a value of 19.2. By the end of the optimization, we have a new value of 6.97. Here we have a summary of the change in design variables. You can see that x1, x2, and x3, which represented the areas, started at value of 1. The thicknesses started at a value of 0.2. By the end, you can see that there has been a change for both the thicknesses and the areas. For example, the first area is now 0.86, whereas before it was 1. One of the thicknesses is now 0.044. Another thing you might want to review, the normalized constraints section. It's always good to have a normalized constraint less than 0.003. Here, since we have negative values, this is less than 0.003, so we know that the design is being satisfied for all the given constraints. Here, towards the end, we do start having positive values for the normalized constraints, but remember, by default, the tolerance is 0.003, so as long as this value is less than that, we have a design that is satisfying the constraints. So this optimization looks good. Let's see where else we have to go with this. Let's go ahead and look at the results in my pre-post processor. If you look in the downloads directory and the Nastran working directory, there is a new OP2 file. This OP2 file has results for the initial design. So that's the design before you ever perform optimization. It also has results for the last and final design cycle. So this would be the optimized structural results, if you will. So here what I'm doing is I'm going to read these new results, and we'll go ahead and click apply. And then here we'll go ahead and look at the first natural frequency for the initial design. Here in the right-hand column, now we have two sets of data. The first set of data ends with a marker named D0. So this corresponds to design cycle 0, which is also known as the initial design. So here we know that the very starting natural frequency was 25 hertz. So here, let me go ahead and plot the mode shape while we're looking at this. The next set of data, you can see the final marker is D6. The D6 corresponds to the last design cycle that you find in the plots. So here we know that the new natural frequency is 19.943 hertz. Now, why is this important? This is important because the optimizer has made an attempt to minimize the areas and the thicknesses while making sure that the constraints are satisfied. So here the thickness was minimized until the limit where you obtained a natural frequency of 19.9 hertz. You see it's slightly violating the lower bound of the natural frequency constraint, and that's due to tolerancing. So here for our needs, this is an acceptable thing to have. So going back here, you'll see that explains why we have a slight positive normalized constraint. The constraint was actually defined as 20 hertz, and that's given here. But the final optimized model has a natural frequency of 19.943 hertz. This again is a okay discrepancy just because of the tolerancing. One other thing I want to show you, sometimes you might have to carefully review some of these responses. For example, if you've configured an A1 response, so let me go ahead and see if I can find that response here somewhere. Here, for example, if you've configured the A1 response, at some point you want to confirm that it's giving you, or it's using the correct value that you intended. If you open the responses app, which is located under the results section here in the bottom left-hand corner, you can upload the F06 file from the optimization. There will be a lot of data here. Here, this first row is for label A1. So here I am told that the weight of the entire structure was initially 109. But then we had this objective that said that 109 minus 90 should give me a new weight to use. So here, this equation is corresponding to R0. So if we look back at the table, we see that R0 is in this row. You notice that the value here given is 19.2. So let me go back and look at this and see what else do I want to review. All right, so here, just so we are believers of this, remember the equation. A1 minus 90 gives me R0, and here it's supposed to give you a value of 19, and that's in fact what I have here in the table. One last thing with the plots. Here you'll notice that these values for constraints are not actual constraint values. This value is not an actual natural frequency constraint value. This is a normalized constraint value. What you can do with the table is click on maximum constraint for each design cycle. This can be used to track which specific constraint is being used in this plot. So for example, this negative 0.2947 value, where is that from? Here, if I look at the table for the first initial design, this is where I find my negative 2.947 value. And this is a normal mode response. Specifically, this is the natural frequency for mode 1. And you can see this is done for design cycle 1, 2, 3, 4, 5, and the final design cycle. So here, let's go ahead and move this to the left, and we'll go ahead and move this plot to the right. So again, this normalized constraint plot is not plotting natural frequencies. It's plotting its normalized constraint values. This table can tell you which normalized constraint values those are, and it can actually tell you specifically what the values of the constrained value is. For example, we started with the natural frequency at 25 hertz. Here back in Patran is 25 hertz. And then minimize the natural frequency to 22.4 hertz, 20 hertz, 20 hertz again, 19.9 hertz, 19.9 hertz. And then towards the very end, we had a constraint value of 19.9 hertz. So that's how you interpret some of this data. Let me go ahead and go back to this and see if we can start summarizing what we've discussed. So as intended, we were able to minimize the weight from 19.2 to 6.97 pounds. We also saw that the natural frequency, which started at 25.9 hertz, I believe, this was then reduced to 19.9 hertz, which is approximately 20 hertz. Here you can see from the diagram, I've already gone ahead and processed what the new structural dimensions will look like for this built-up structure. And now, what else do I want to look at? I don't think I did cover this, but if you want to know what the objective value is, of course, you would just look here at the objective plot. We started off with 19.2, then we ended at 6.97. The last thing I want to leave you off with, if you remember, we started off with this PDF file. This PDF file is outdated. If we look at both the PROD entries, they're using old cross-sectional areas of 1.0. If you look at the thicknesses too, these are old thickness values. So what we need to do now, we have to update these values. So here, I'll go ahead and make a copy of this file and I'll move it to the right. And then I'll rename this file, update it. In the same directory where the optimization was performed, there is a new file called the PCH file. This file contains the same PROD and P-shell entries, so here are the PRODs and the P-shells. But now the data has been updated to have the new cross-sectional areas and the new thicknesses. So here, if you look back at your plots, and look at the change in design variables, you see here, for example, the thicknesses are now 0.044 and 0.0256. So here back in the PCH file, you see those same values, 0.044 and 0.02526. So what we can do is update the original PDF file with these new values. So here, what I will go ahead and do is I will remove the old P-shell entries, and then I will remove the old PROD entries. And then what I can do is just copy and paste all of these new entries. In this case, I'll cut them out. And then I can simply go ahead and just paste it here. And then I'll close this old file. And then I'll save this new PDF file. And there we have it. This PDF file, the one that's on your desktop, now has the new updated parameters, areas, and thicknesses for the optimized model. So there you have it. That's the end of the tutorial. And before we close, just a quick reminder, if you are a professional engineer and would like additional training, if you would like some advice from me, if you have any general questions, you can contact me at this email address. If you are a student and you would like access to the Nastran Solution 200 web app, you can also contact me at this email address and I will be more than glad to grant you access. Access is available to professional engineers also. With that, I'll go ahead and stop it there, and thank you so much for watching.